Hi there. My name is Neil McIsaac, and I'm a Microsoft Technical Trainer. In this video, we'll be focusing on optimizing our model training. We'll start by looking at how we would run a training script as a command job. We'll then cover how to track model training with MLflow and jobs. And if you've seen a previous video where we introduced MLflow, we'll go into a little more depth here. And then, and I think this is the big takeaway in this video, we'll cover how to perform hyperparameter tuning within the service. To wrap things up, we'll also show how to run pipelines within the Azure Machine Learning. So let's get started. At some point, after we complete enough experimentation, which is typically done using notebooks and compute instances, we need to start thinking about moving our code over into a production scenario where we'll build our models using larger amounts of data as well as need larger compute to process it. But most importantly, our code needs to be scalable, repeatable, and ready for automation. So although notebooks are ideal for experimentation and development, scripts are better for production workloads. In Azure Machine Learning, you can run a script as a command job. And when you submit a command job to run, you can configure parameters like the input data and the compute environment. The Azure Machine Learning service also helps you track your work when running command jobs, so we can compare runs or investigate problems later on. If we used a notebook to do our experimentation and development, which is very typical, we'll need to convert the notebook over to a script before running it as a job. Some people actually use scripts right from the beginning to do their experimentation development, but most people would find working with scripts difficult, and so they use notebooks because it's easier to work with during the development stage. So if that's the case, we'll need to do the conversion between the notebook and the script. We'll need to do a couple of things, though, before we can run that code simply as a script. One of the first things you'll want to do is to remove any non-essential code, since ideally, scripts are streamlined to do the work and not really intended to be interactive like the way we would use a notebook. So things like showing graphs can be easily removed from those. The next thing we probably want to do is refactor the code into functions. I think an easy way of describing this is simply to make the code more readable, and functions can be an easy way to do this. Of course, before we do anything in a production environment, we test, 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 test. Now in this case, it's probably easiest to test your script within a compute instance by simply running it inside the terminal session. Hopefully after all of this, we have a production level script that's ready to go. Once we have our script ready, we can then run it as a job. So jobs in the Azure Machine Learning service come in three different flavors. We have a command job, which is used to execute a single script, and it's probably the most typical type of job that we use. We also have what's called a sweep job that is designed to do hyperparameter tuning, and we'll look at hyperparameter tuning later on in this video. And lastly, we have a pipeline job, which is designed to run multiple scripts or components, and is usually ideal for doing a series of steps and coordinating the logic flow between all of them. So when we go and configure a command job, we need to set a number of things in order for run. First, we need to set the code parameter. Now this is actually the path to the folder where the code lives, while the command property is used to specify the file to actually execute. So between these two parameters, you should have a complete path to the script that we want to execute. We also need to specify the environment, which will specify any of the packages and libraries that our script might need to have to make sure that they're available in order to make sure that everything executes properly. Next, we need to specify the compute that'll be used to actually run the script. We also need to set the display name for the job so we can identify it in the interface layer. And we also need to set the experiment name so we can group those related jobs together under the same experiment. Ideally, we want our scripts to be as reusable as possible. A great way to do this is by making sure that our script can accept parameters so that we can change settings during different executions. Since our script is based in Python, we need to import the argparse library into the script. and then use the argument parser method to define the arguments for parameters. We also need to specify each of the parameters in the script, including setting the name, type, and default value. Those steps are done within the script itself. The next thing we need to do is to make sure that when we call the script, we set the parameters by name and set the values to what we want to use to run our script. In the example in this slide, you can see that we're calling the Python train.py script. And we're setting the parameters training data to the diabetes.csv file and the regularization rate, which is just here as reg rate, to a value of 0.01. So let's jump over to the workspace and see how to create a command job. All right, so let's start things off here with going over to a compute instance. And let's get into a terminal session. And on this one, so what I want to show you here is we have a notebook, right? And think very typically, I have a notebook, I've been doing experimentation. In this case, it's to do a classification model. I've been working with it a bunch. Let me, before I forget, let's switch this to the Azure ML kernel for this. So this is just a standard notebook, right? Where we're grabbing the data, we're splitting it up. We are going to train the model, do all these things. We can evaluate the model just below this, and figure out a bunch of the metrics for it. We're also plotting the ROC curve, right? So you see that it's going to show up on the screen. Now, the thing about this, and here's kind of the goal, is that we'd like to, while I'm talking here, I'm going to run all this. We'd like to take this and turn it into a script. So just to show that this does work, right? So you can see the data, it's splitting it up, doing all the stuff. And at the bottom of this, we go down, we'll see that not only does all the cells run, but also we're going to have the accuracy is in here, the AUC, we're going to have the plot at the end of it, right? So the thing is, if I were to take this and move it over to a script, I probably don't need this image, right? Maybe I want to save it or something. So the point is, I'm probably going to have to take this code and change it. So one of the first things is, this is a pretty good feature, is we can take this notebook and just simply export it as a PY file. And it's going to take all the code and just export it as whatever file name we want here. All right, so let's get a slightly better name. And if it exists, we can overwrite it. So that's going to be pretty good. Let's do the export. So let's create that. And as soon as we do that, as soon as that goes, let's go. Let's go over and look at what it actually created, right? So here's the export. It really is all of the sections that we had in code exported out. Now, at this point, though, remember that the goal here is to be able to take what we had in the notebook, which is designed to be much more interactive, and take this code and make it so that it can run on its own. So, high level, we probably want to go through and fix it up. We can run it, so we can save and run this to make sure it works okay. So pretend I cleaned it up. I just want to point out that it's still doing everything, right? It's reading the data, splitting the data, training the model. It's doing everything, but notice I don't see my plot. I don't see that part because it just doesn't go out to the terminal interface. So I could probably go back and remove that code. But the good news is that I can see that this works, right? And that's kind of one of the important parts. Now, I could take that further and say, well, let's make this script much nicer and all that, but we'll pretend we did that. So let's go over to a different PY file that we've sort of done all that already. So you can see on this one, we have things broken down into functions, right? Instead of just one simple PY script, we have a main function here, and the main function has all the function that's calling. So get data, we're going to split the data, we're going to train the model, we're going to evaluate that model, and then we have the definitions of all those functions, get data, right? So the first one, and right down here, split data, right? So we see all the functions in here and all the code that goes into it. So this is maybe a little more practical for a production level script. We also have arguments. Remember that ideally our script should be able to be parameterized, right? So I can pass parameters to it. In this case, it'll accept a training data argument. And the way to, so you'll see like path and variables going to get used through this, but way down the bottom, right, let's come down here. You'll see that it's basically, when we set up the script, and this is just kind of standard Python here, we're using the parse args function to parse all the arguments. This is standard Python. And then we're passing those arguments into like the main method and whatnot. So that parse args is set up here to have that training data and regularization rate as two parameters, and where there any defaults with them and whatnot. So the training data one doesn't have any defaults, right? Just the regularization rate. And so what happens if we don't supply that, right? As kind of a question. So we're gonna check that out here in just a second. So let's pretend we're still testing this. We're gonna save and run it. And what we get is a big error, right? If you look at this, so you get a trace back, being thrown from it. And why is that? Well, the command here, Python and then our py file, if you really look at this, it's invalid file path or buffer object. It's like, okay, if you really dive into this, it's because we didn't supply that parameter on it. So when we run this script, we need to run it and pass that argument to it. So let's do that, right? So I'm just gonna make sure we're in the right directory here. Actually, now that I'm looking at the directory we're in, since I'm already typing, I'll put it in anyway. We're kind of there already, so that's fine. We're in the right directory. So let's run this Python command. So it's going to be Python, and then our py file, if I can type it. If I can type it. So train model parameters py. And then at the end of this, we're going to supply the argument that we need. In this case, it's going to be the training data, which is going to be the diabetes.csv. And, oh, we got an error. Let's see. That should be okay. Oh, I think I see it. So it was just another typo. It was diabetes. Let's get that R out of there. And let's just run that. Oh, fix that up. There we go. If only I could type. So let's run that, and you'll see that it reads the data, splits it, does the training of the model, all of the things that we're kind of looking for, thumbs up. And now it's parameterized as well, so I could actually pass, different training data to it. All right. So that's pretty good to see that we now have a script. Okay, so what next, right? We have this production level script. Let's go over and look at command jobs, right? Because if we're doing training on a routine, scheduling, etc., we want to put everything in command jobs. So let me do just a little quick plumbing here first to make sure we're all signed in, and we get the ML client real quick. Okay, so it jumped around there a little bit. So let's talk about command jobs. Command jobs, right? Earlier when we were talking about it, we just have a bunch of parameters that we want to set on it. So let's go down and look at that in the code. And you'll see that what we're creating is a command style job, and it's just the keyword command. The code parameter, that code argument, is the directory that we're talking about. And then the command argument is actually the py file that we need to point to. It's really the command, right? So Python space and then the py file. But it also has any parameters that we might want to pass. Now in Python, you might make this a lot more dynamic, so it's not hard coded here, but this works. The rest of this, environment, right? We talked about those earlier in the course. So we can specify that. We can specify the compute that it's going to run in, so the rest of the bits of the job. And the big part of this is that, that script that we had that we just turned into a production level script, we can now use this in a production environment. So we're going to call the creator update command for jobs. And from that, we get the URL being returned back. So our job is now submitted and it's off and running doing the training. All right, so if we go look at it, right, oops, we'll see that the job is there. So diabetes train script, it is queued, right, doing the work. Now at this point, because the job is using the cluster, it is going to be spinning up that cluster to go and do everything, which is going to take a few minutes for the cluster to go. That's just because that's the compute that we selected on it, but it will actually go and complete the job as needed. So and it's going to do all the steps that we just saw, just in a much better environment, because we can do things like schedule these, right, which is going to be a little more critical, or call them on demand, and it's all configured for us. Okay. So with that, let's go back to some content. In a previous video in this course, we introduced ML Flow. Since we're discussing how to execute jobs here, which are going to be script-based, it makes sense that we would use ML Flow to track our model training. So let's take a closer look at that. Just as a reminder, ML Flow is an open source package that helps us to manage the machine learning lifecycle. If you want to use ML Flow in any of your code, you need to ensure that the ML Flow and the Azure ML Flow packages are both installed into your compute environment. These packages are already installed on the compute that's provided by the Azure Machine Learning Service. So lastly, when we're using the ML Flow library, we can choose to enable auto logging by using the mlflow.autolog function if our algorithm supports it. Or we can use the logging functions library to manually log data from our script. Let's take a closer look at how to configure logging with ML Flow. If our training library supports auto logging, then it's just a matter of enabling the auto log function, right? We just basically call it and we turn it on. All of the parameters, metrics, and artifacts would be automatically logged without us having to do anything else. So for example, libraries like TensorFlow and PyTorch, they all support auto logging. So it's just a matter of turning it on, which is great. If our training libraries don't support auto logging, or if we would like to log additional information for a training library that does support auto logging, we can add calls to these ML Flow log methods to record the data. The first one, log param, can log a key value parameter, so we can see what parameters were set when we executed the job. The second one, log metric, can log a single key value metric, and in this case, the metric must be a number. This would typically be used to show metrics from a model like accuracy or area under the curve. The last one is log artifact. This one is used to log a file and is typically used to record things like plots as image files. So for example, if you wanted to record something like the area under the curve plot as an image, you can do that with this method. Once we run our script and record things like metrics and plots, we can see the results in the Azure Machine Learning Studio interface under the details of the experiment run, where we can see the log parameters under the Details tab, we can see the logged metrics under the Metrics tab, and we can find any of the logged artifacts under the Images tab. If we want to retrieve the experiment runs programmatically using the Python SDK, we can also do that. We can start by listing all of the experiments using the search experiments method in the ML Flow library. Once we retrieve the list of experiments, we can use a specific experiment ID to call the search runs method and retrieve all of the details of that specific run. All right, So let's take a moment, see how this works with a demo. All right, so let's talk about using MLflow here. So I'm going to start off with this notebook, right? Using MLflow to track jobs, and yeah, so basic notebook to start off with. Where I already ran the beginning where we get the ML client and everything, and we're going to grab our data. So for the script files, we're going to write out, and the very first thing that we're going to do, so after we do that part, writing out to the source directory, is we're going to write out this script file, right? So this is just generating the file. And inside of this, because we're using MLflow, we have an import statement for it to start things off with. As we come down a little bit, this is just doing a kind of a typical training model. So we get the data, we split it, we train the model, evaluate the model, all that's still there. And all of these are within functions, of course, right? So right here, when we train the model, right below this, we have mlflow.logParam, where we're going to log the parameter for this, right? The hyperparameter. So the regularization rate, right? And the value for it. And of course, we're using a logistic regression model for this. So that's going to return the model. And then when we evaluate the model, we can log the metric that we collected from it. So this first one, we have the accuracy, and then just below this, mlflow.logMetric, the AUC, the area under the curve. And the last thing we're going to do when we evaluate, we're going to plot the ROC curve. And since we're talking about MLflow, just down the bottom, it's log artifact. And then we're going to log the artifact, the ping file, the PNG file. And what this should do is show up in the interface, and we'll show that in a little bit. So the rest of this is just doing the parse args and everything that we saw in some previous commands. So let's write this out. We'll create that py file, and let's go down. That's all written out, and let's queue up a job to do all this. So again, we're just making it go. The big difference on this one is that this is actually marked up with MLflow. So let's run it. And of course, we have a job that we can monitor now. And this is going to take a little bit, so let's jump over to it. And once this loads, you'll see that the job is queued, right, currently. So it's going to take a little bit because remember, command jobs, this is set to the cluster needs to start up, it needs to do the work, all of those things need to happen. So we'll wait for a little bit. Well, let's refresh, see if it's started to run yet. Not yet. There we go, so now it's running. All right, see there, right there, that's running. And we could try being patient and keep clicking the refresh button. Usually at this point, we'd probably go get a coffee or something. Go get a beverage, all right, because it does take a little bit, even though it's a pretty small job for this. Since this video has been pre-recorded, we've sped up this section to save you a bit of time waiting for this to complete. Go. All right, we just saw the notification come in that it's completed now. So if you see a refresh, it's now completed. And now we can go look at the outputs, right? So let's go over to output and logs. And on this one, we see that in the standard log text, we see the output, so it did all of its work. But what we're a little more interested in are the MLflow artifacts. So you can see the ROC curve PNG, that was one just from the output. But if we go over to images, right, because we logged it, logged the artifact, we actually see it here now. Right? So anything that's there for artifacts there, for metrics, we see the metrics that we logged. So the accuracy and the AUC, the area under the curve, are both logged in here, so whatever metrics we want. And on the overview page, we see the regularization rate way over here under params, right? So that one is when we did the log param right at the beginning of that. All right, so as you can see, we can log all kinds of things with MLflow. All right, so let's jump back over to the content here, and we'll talk about hyperparameter tuning, which is awesome. So one of the biggest challenges that a data scientist has with respect to training a model is deciding on which algorithm to use, and also the hyperparameter values to use. We need to figure that out so we can try and produce the best model. A hyperparameter represents individual settings that we would set on a training algorithm. So, for example, maybe the regularization rate to set on a logistic regression algorithm. The reason these are not referred to as parameters is because within the machine learning space, parameters actually refer to the values determined from the training features. So to avoid any confusion, we use the name hyperparameter to refer to the values that we would set on a training algorithm to execute. When we're talking about hyperparameter tuning, we're configuring the values that we want to set a specific hyperparameter to, including using different values to create different models, so that we can compare the impact of different hyperparameter values on the model training. In the Azure Machine Learning workspace, we would use a sweep job to tune the hyperparameters. We would start by including an argument for each hyperparameter that we want to vary within the training script. We would then configure and run the sweep job with each hyperparameter configured with the different values for that hyperparameter that we want to use to generate multiple models with our job. After we do that, we would run our sweep job and simply view the results. So let's take a closer look at how to define the values that we want to use to tune our hyperparameters. First, we need to decide on whether we want to use discrete or continuous hyperparameters. Discrete hyperparameters are used when we set the hyperparameter to a finite set of values like 1, 2, 3, and 4. And continuous hyperparameters are used when the value could come from an infinite set of possibilities. For example, when we select a value from a range like any decimal value between 0 and 1. The settings that we use to define the set of values to use is referred to as a search space. When we configure our hyperparameter tuning, we need to select the type of sampling method that we want to use. The Azure Machine Learning Service supports grid sampling, random sampling, and Bayesian sampling. Grid sampling can only be used on discrete hyperparameters and will try every possible combination of the values that we specify. So for example, if we configure a hyperparameter to use 5 specific values using grid sampling, we would produce 5 different models, one for each of the values. If we had 2 hyperparameters and each of them were set to 5 values, and again using grid sampling, we would end up producing 25 models from the sweep job because we need to go through every combination of those 2 hyperparameters and build models from that. So each parameter, each combination we need to do. Random sampling behaves just as the name implies, in that it will randomly select a value for the hyperparameter, and this can be used with either discrete or continuous sampling. The last method, Bayesian, is a sampling method that will choose hyperparameter values based on the Bayesian optimization algorithm. The idea is that it selects values that will result in improved performance based on the previous selections. This one can only be used with the choice, uniform, and Q-uniform parameter expressions, and it's not possible to use it with an early termination policy, which we're going to look at next. Early termination policies are used to limit the number of trials that our sweep job would run. The idea here is that as we're running a lot of jobs, if we determine that a model is not producing better results than the previous trained models, we can stop wasting time training the model by stopping it early. This can save us valuable compute, which will translate into savings. We do have to consider our search space and which sampling method our sweep job is configured with, because early terminations are not supported for all of them. That being said, if we have a large number of hyperparameter values, especially When we're using continuous hyperparameters, we could be set up to create a very large number of models during a sweep job. So in that case, configuring an early termination policy would be an ideal way to limit the number of executions that we would have. When we configure an early termination policy, we need to specify which policy type we're using, as well as the settings for that policy. All of the early termination policies have two main parameters that we need to set. The first parameter is to configure the evaluation interval, which specifies how often we'll evaluate the policy. So for example, an evaluation interval set to 1 means that we'll evaluate this policy on every single trial. The other parameter is the delay evaluation parameter. This parameter specifies a number of trials to wait before we start evaluating the policy. This parameter is useful since we probably don't want to evaluate our policy when we only have a few trials that have been executed. We just don't have enough information at that point to compare the newer trials to. The three policy types that are supported are bandit policies, median stopping policies, and truncation selection policies. Let's take a look at an example of each one of those. The first example is a bandit policy. Bandit policies will stop a trial if the performance is too far away from the leading trial performance. Now, when I think of this policy, I think of the old Western movies where there's a bandit that just robbed the bank, for example, trying to get away on their horse with the sheriff and the posse trying to chase them down. If the people chasing them get too far away, they might as well go home, right? Because they're never going to catch the bandit. Only the people that keep up with the bandit should keep riding. So in the example in the slide, we see that we're configuring a bandit policy and specifying a slack amount of 0.2. The delay evaluation of 5 and an evaluation interval of 1. What this means is that any trial that falls out of the 0.2 margin that's specified in the slack amount will be terminated. Because the delay evaluation is set to 5, we won't start calculating this policy until after the 5th trial. After that, the policy will be evaluated for each trial since the evaluation interval is set to 1, so each time. And as you can see from the two plots, on the left-hand side, the 6th trial was within 0.2 of the accuracy of the best trial, and so it was kept. But on the right-hand side, the 6th trial fell below this margin and was terminated early. Keep in mind that it's possible for a later trial to become the new bandit. In other words, a later trial could become the new leader, which will affect where the margin is moving forward. The next policy that we're looking at is the median stopping policy. This is similar to the bandit policy, but the calculation of where we draw the line is a little bit different. In this case, we calculate the median of the performance metric, and any of the trials below this median line will be terminated early. In this example, we see that we only need to specify the delay evaluation and the evaluation interval parameters. The other thing is that this policy is more likely to change since the median value will change as more trials go above that line. The last policy is the truncation selection policy. This policy specifies a truncation percentage. And what that means is if a trial's performance metric is within the bottom X percent, in this example, 20%, it's terminated early. You can see within the plot of the trial performance on the left side that the performance of the 5th trial is not in the bottom 20%, and so it's kept. On the plot on the right-hand side, since the 5th trial is in the bottom 20%, it's terminated early. So setting early termination policies can be a great way to optimize the compute that we'd use to execute your sweep job. Now, let's take a look at a demo on how to do hyperparameter tuning. All right, let's start things off with looking at the training script that we're going to sort of base everything off. So this is still just a typical training script. where we set up the source. So we've seen this style before, where we want to play with the script files. We're going to write out our training py file, our training script. And there's really nothing different here. So I'm going to just do this. It's going to read the data, split the data, all of these things that we did before in here. So training the model. There's nothing really that special. With this one, you see that the regularization rate, so the reg rate, is here under args, just to note that it's an argument. And we do have things like the ML flow statements and all that in it. But our focus here is really about doing hyperparameterization. So the first part is really say, hey, we have a command job where we want to go run that script. And so being able to configure the hyperparameter, right, that we exposed as an argument is really just setting up the command job for this. So the code and the command is kind of the same thing, but you see the regularization rate right here as an argument. So making sure that our script supports it, and then we can pass a value to it, right? So for those inputs, we can set a value for it. Now, the catch with this, let's run it because that's going to spawn a little bit of work. The catch with this as a data scientist, we put one value in here, we run it, we see the results, we go change this rate, we run it again with a different rate, and look at those results. We run it again with another rate. How many times do we have to do this and to see all these different values? So this is really, I think, kind of establishing the point is we have a hyperparameter, but we're not really taking advantage of being able to tune it that effectively. So let's go down, right? So yeah, that's we do have a job that spawned to that, of course, but let's go down and talk a little bit more about actually doing the tuning part. So the first thing we want to do is set up what we refer to as the search space. And this is when we set up the parameter, the hyperparameter, to be set to a number of values. So in this case, we're using the choice function to say one of these three discrete values. So the choice function will give us discrete values. So 0.01, 0.1, and 1. Three different regularization rates that we want to run everything for. And we are going to set up a sweep job, right? So we're going to see that in just a second. So, so let's get that all set up. All right, let's run it. And let's come down and configure this sweep job. So one of the things about this is that, we have the parameter that we just set up, the hyperparameter that we just set up. When we go to pass it here, we want to specify what type of sampling we're going to do. In this case, it's going to be grid. And if you remember, grid says we're going to take every combination of values. So in this case, we only have one hyperparameter with three values. So we are going to get three models from this. We can set limits on this for how many trials we're running through, of course. But I think the big point here is that is what that hyperparameter is really set to. So let's run that. That's going to configure our sweep job. All right, so that should be all good. Let's submit it. All right, so that's going to be the creator update for the sweep job. So now we can, we have the link to monitor it. So let's go over and yeah, I think we're pretty good to go over and look at monitoring here with that. All right, so it does take a minute to go. So, all right, let's go over here. It's not remember the jobs are not the fastest thing. So we see that they're running now, which is good. Now, depending on how many parameters we're actually supplying to this, we could potentially have a lot of trials, a lot of things going on for this. And so with this one, if we scroll down on the trials page, we can actually see the different trials running, but look at the regularization rate. Notice how it's running through the values. Now we only see 2 here because we set a limit of the number of parallel trials was going to be limited to 2. That was when we set up the sweep job, right? So these are both there. And once one of those finishes, it would actually go and spawn the 3rd job and kind of keep going through it. Now do keep in mind, if we had a lot of these, like different parameters, we would see a lot more jobs, child jobs getting spawned for that. All right. So that's pretty neat. That's basically hyperparameter tuning. There's a lot more to configure the parameters, but let's go back to our content so we can get going into components and pipelines next. In the Azure Machine Learning Service, a pipeline is a series of machine learning tasks in which each task is implemented as a step. Basically, this is a form of a workflow. We can use pipelines to coordinate machine learning tasks like model training and testing. Components are a foundational part of creating pipelines, since these essentially represent tasks that need to be completed. And we'll use a series of components in a pipeline to create a job. Components are reusable scripts that are packaged as a component. The challenge here is deciding on how to break down a larger process into smaller pieces so that we can much better reuse those pieces into other processes. Some examples of components might be a component that trains a model, or one that prepares data in a specific way for your organization, or maybe it evaluates a model that's been trained. The advantage here is that since it's basically just a Python script, the component can do a task that is specific to your organization. In other words, if there is a specific way that data needs to be prepared in your organization, you can create a reusable component that other data scientists can use, which can help to ensure that the data is processed very consistently across your organization. As I mentioned, a component is basically a script, but we need it to play nicely with others within the machine learning service. So we need to take our script and add metadata that will describe the component to the machine learning service so that others will know what it is, and we need to define the interface for the script. Remember that the component will be part of a pipeline, which means we'll have many components doing the work, and one component will need to pass data to another component. The interfaces that you define on your component will define what data can be passed in or out of your component. This will also help restrict what components we can connect to. In other words, if we connect two components, the output of one component needs to match the input of the other component. In order to create a component, we need to have the script that does the actual work, as well as a YAML file that will define the component metadata, interface, and configuration of that script. Once we build the component, we'll need to register it in the machine learning service. We can use the Studio interface, or we can register the component using the Python SDK by using the create or update method on the components class, which is what you see an example of on the slide here. Once the component is registered, we can start using it within a pipeline. So let's talk about pipelines. Pipelines are really a form of workflow, but let's take a step back for a second and look at the bigger picture. Could we do all of the steps that we need to in a script that runs as a command job? Sure. Could we separate our command job into multiple scripts and have something like a master script call all the child scripts to do the workflow? Absolutely. So why would I want to go through all the trouble of packaging my scripts up as components? Well, if you leave everything as just scripts, what about things like version control? Or do I just update the script right in its place? Or if I was going to call a script, how would I discover what parameters to pass to it? What if I had a script that called a bunch of child scripts? How easily would it be for me to understand what's going on in it, especially if I wasn't the author that made it all? The point is that by packaging our scripts into components, we get a much better reusable package for our script. And then we can use it in a pipeline. We can see it more graphically, which helps others to understand it. If we focus entirely on using just scripts, they can actually get pretty messy fast. Also, components support versions, so we can track changes much better with them. We can define our pipeline programmatically using a YAML definition, or we can do it in the Python SDK using the pipeline function to create the YAML file for us. We can also create pipelines visually in the Azure Machine Learning Studio. Of course, once we build a pipeline, we can then run it as a job. So pipeline jobs are really just jobs that simply run a pipeline. Of course, we can schedule them to run on an interval. If we want to schedule them using the Python SDK, we can do that. We would simply use the job schedule class to assign a schedule to the job. And if you wanted that job schedule to repeat, we would use the recurring trigger class with the job schedule class to create a recurring schedule using the Python SDK. So let's jump into a demo and see how we can use components and pipelines. All right, let's start things off with we're going to use a notebook for this, but start things off with building our components and pipelines. We're going to use a notebook to do all of this. So all the plumbing that we've seen before, we're going to get that the source folder created. And the reason is because we're going to make a couple of scripts here. So the prep data py file that I just highlighted, this is a pretty standard, prepping of the data. So getting the data, cleaning it up, doing any normalization, and then putting it out as a CSV. You notice that we're not training or evaluating a model for this. So this script is all about prepping the data. And it will accept an input data and output data parameter argument. So both of these here, they're both of type string. But this is going to say, like, here's the data that we need you to prep, and this is where we want you to output it to. So this is all there. Let's write this out and get that py file. And once we do that, we can come down to the next py file that we want to do, the next script file, and this is going to do the model training itself. So in the main in this, we're going to get the data, right? Again, notice it's set as an argument. We're going to split it. We're going to do the training. And further down, same idea. We have the functions to do this, like to train the model, to evaluate the model. But you will notice that we do have arguments for this, right? So look at our parse args. We have the training data that needs to come into it. We have the regularization rate and also the model output, where to put the model that we're going to produce. Where should that go? So another script that's parameterized. And those are both, I think, pretty simple. So let's get that built. And now let's start looking at the magic. So this is where we're going to take those scripts and we're going to wrap it into a component, right? So what we need to do for that is really define the metadata. So if we take the prep data, that script, we're going to create a YAML file to really reflect that. So we're going to give it the name. This is just prep data to match the name. We'll give it a version. We'll specify all the inputs and outputs, right? So you see the input data. You see that it's of type URI. Output data is a folder. So right there is the URI. Right here is the folder for the output. So this is defining those parameters. Now this is the YAML to define the component. The environment, and of course we need to specify what script we're pointing it to. So that's the prep data script. And then how the input and output match the arguments for it. So it's just a definition. This is simply going to write out the YAML file. So I ran that and that's all produced. We're going to do almost the same thing with the train model. The py file, we're going to make a YAML file for it. And again, it's going to have its inputs defined, potentially with defaults, its outputs defined here, and then the actual Python command to say, and this is what we're going to run for this component. So components are really just a wrapper around these scripts. And when we have these wrappers, what it allows us to do is to go over to the Azure Machine Learning workspace here, and we can load them into the environment, right? So say, here's the YAML file with the definition, like make this component basically available to other things in the Azure Machine Learning workspace. And that's all it really takes to do that. Now, once we have that, we can go further down into building a pipeline. And if you recall, whoops, my bad. Habit of double clicking those. But if you recall, pipelines are really just a series of components that we're going to run together. So it can shorten this script quite a bit. But more importantly, because we made those components, this can be a little easier to reuse those. So this one, we're making a diabetes classification pipeline. where we call the prep data, and right below that, the train decision tree, right? And these are really the references out to those two components that we were just talking about. And we're going to wrap these up into a pipeline. So we have a decorator here to say this is a pipeline definition for this. And so let's run that. That's just really going to, kind of create the definition for it. And then let's see. Yeah, so, I do want to mention that, the prep data here. So this prep data is going to return clean data. I knew I was forgetting something. So the clean data, if you look at the input for the train decision tree, it's that clean data is being passed to it as one of the parameters into that train decision tree right there. So this is one of the ways that we can have components to say the output of one component can be the input of another component. All right, so that's all run. And it's going to we're going to return, the outputs from these, so we can see them later on, and define that job, right? So yeah, I ran that. All right, let's come down a little bit. Let's look at running, just showing the pipeline job, the definition for it. We can see all of the metadata around the pipeline job definition, right? So it's really, from here it's type pipeline job. It's saying, the inputs for it, then the outputs for it. So it's really, this is really simply the definition for it. And the jobs inside of it, the clean data job, the definition for it. So think all the components that are really in it to go and run. And all these components can have a lot of their own settings for everything as well. So that's pretty good. Now, to play around with this a little bit, what this is going to do is we're going to change a few things. I'm just going to highlight this one, default compute and default data store. So, and notice their settings, AML cluster and workspace blob store. So let's run that. What this is doing is changing the definition for this. So if we start looking through this, we should see these different settings, right, for how this pipeline job is going to run. So it's still just simply a job definition. There's just typically a lot more going on because of all the components. So in this one, let's see if we can find one of them. I know a couple of them are at the very bottom, so see if we can spot them. All right, yeah, we'll just use the ones at the bottom here. So the two at the bottom, default data store and default compute, that's the settings that we set. And so workspace, blob store, and AML cluster. So you notice that, yes, we can do it. All right. It's still a job. We still need to submit it. It still needs to go against compute and do all the running. So let's get that going to do everything. And of course, those components are actually like child jobs within it. So here we go with the run. And this will take a little bit to actually go and do. So you've seen that jobs can take a little while to go. I think the big thing here is that we're able to take those scripts and wrap them as components. And then the job, we're not going to stick around to watch that job go at this one. It takes a little bit of time to do that. So hopefully that makes sense why we might want to take those scripts and turn them into components and start using pipelines for it, because there is a certain amount of reusability when we do that. Okay, let's jump back to the content where we're going to just do a quick recap about everything that we've seen in this video. So let's move over there. And that brings us to the end. I hope that this video helped with your understanding of how to build and use scripts to support jobs, as well as how to use ML Flow to track those jobs. Hyperparameter tuning and how to configure a sweep job was also a big part of what we covered in this video. And in the last part, we spent some time on how to build components and pipelines. I hope that we see you again as you continue through this training series. Thank you for watching.